Hello and welcome to another activity in our study of scientific computing with C. So in today's activity we would be looking at this. So the activity says that we are to write a C program for the Newton-Raphson bisection method and the second method to solve the following nonlinear equations. So we're given x cubed minus x minus 1, and then f of x to be equal to x cubed plus 2x squared plus x minus 1. So what we are going to do, we are going to divide this activity into 3 sections or 3 parts so that the videos will not be too long. So we'll first start with the bisection and then continue with the Newton-Raphson in another video, and then the second in another video. Now the way we are going to go about this activity is that I would be using one of the nonlinear functions and then let you do the other one on your own or try out using the same approach. It will still work. The same approach will work for all the nonlinear equations. So I'll just do one in the video and then let you do the other yourself. Okay, so without wasting much time, let's get started. Before we start, as we always do, we first have to go and then plan, right? So considering we are taking, let's say, f of x to be equal to x cubed minus x minus 1, right? And then we have to solve this nonlinear equation using the bisection method. Now the question is, what is the bisection method? So the bisection method practically finds the roots of any nonlinear equation, right, with the assumption that if, let's say, given the interval a b, right, if the root lies between a and b, let's say contains the root, then it means that if you find the functional values, right, the product of the functional values at that side, it should be less than 0. Why is this so? It means that if the root exists, right, in the interval, in the given interval, then f of that root, right, the functional value of the root should be equal to 0. So if the functional value is equal to 0, then obviously we know that, considering the number line, we know that there is -1 and then 1. 0 is between negative and positive. So if the functional value at a is negative and the functional value at b is positive, then obviously if you multiply these two, the answer should be negative. So it means that the product of the functional values of a, the functional values at a and then at b, should be less than 0. If it is less than 0 or if it is negative, then it means that the root exists. Note that we are saying r is between a and b, right? And if we call something a root if the functional value at that point is 0, right? So basically that's that. So to find this, obviously we can't get an exact root, but then all we need is just an approximate root, right? And as we said, we could make use of the computing power of our machines to perform some iterations and get a correct approximation for the roots of any nonlinear equation we have. So first things first, so we first have to declare our function, right? We would first have to define our function. So we'll define our function and then say that f of x should be equal to at x times x, right, and then minus x minus 1. Interesting. Now from here we then, so since we've declared our function, we are now going to look at some other stuffs. So for instance, how do we go about the bisection method. So we first have to check, right, whether the functional value, so given what, let's say the interval, right, so the interval AB and a tolerance, that's our stopping criterion, right? Then we first check, so if the product of the functional value at A and the functional value at B is less than 0, then it means that our root exists between A and B, right? So it implies that our roots exist. For that matter, we would first have to what, determine, right? So compute, let's say the root, maybe our xm, the middle value, to be equal to A plus B over 2. So basically this is the bisection part of the method. So you add the two given interval and then divide by 2. Now after dividing by 2, we then check again, right? Is f of x m, right, is it equal to 0? If f of xm is equal to 0, or f of what, the absolute value, right, of f of xm is less than our tolerance, we want to stop, right? So if it's less than our tolerance, then we do what, we can just say that return our roots, right? Return xm as our roots. Now but then else if, so else if what, now what if f of xm is not equal to 0? Then we would have to check whether f of a times what, f of x m, right, is less than 0. If this is true, then we assign what, bear in mind, if we are saying that f of a and f of xm is less, then it means the root is going to lie between, if this is our xm and then this is our a and this is our b, we are saying that f of a and this is less, then it means our root is going to lie in this region. For that matter, we can now assign this to be our new b, or this is our new a. So we let what, b be equal to what, xm, right? Now else if what, else if f of xm and then f of b, right, is less than 0, if this is true, then we would have to, if this portion and this portion is less than 0, it means our root will lie in this region, right? So if that is true, then it means that we would have to let our a be equal to xm, right, our new a. So we would have to let a new a here and then b here, right? So basically, and then we'll repeat this iteration several times. Interesting. But then what happens, this will only run if the product of a and b, the functional values at a and b is less than 0. So what if the functional values at a and b is not less than 0? So what do we do then? So let's see what we'll do. So first, to check whether, so else if what, the functional values of a and b, so if this is not less than 0, for all you know, maybe f of a could be 0, right? So if f of a is 0, right, or the absolute value at a is less than our stopping criterion, right, then we can return our root to be equal to what, to be equal to a, right? But then it could be f of b to be equal to 0, right, or the absolute value of at b is less than epsilon. If that is true, then we can return what, our root to be equal to b, right? Now the thing is this, what if the product of a and that of b is greater than 0? What happens if you multiply two functional values and you get 0? Obviously it means that you get a number greater than 0. It means that both functional values are greater than 0. and if both functional values are greater than 0, then obviously there will be 0 is not between them. So it means that, so else then we conclude that what the root does not exist, right? The root does not exist, does not exist, right, within the interval. So within what, a and b. So basically that's that. So first we have to define our function, right? Because if we don't define the function, we can't make use of the functional values inside the bisection, and then we would have to perform this several times. So it means that we would have to make use of loops, right? Would have to use a loop, but then now the loop would be using would have to stop based on a particular stopping criteria, that's the tolerance, right? So it means that we can use a while loop here, but then if you like, you could also use a for loop and then make it run a certain fixed number of times. So you can make it run 1,000 times if you want, or 100 times, but then of what use would it be if you could just give it a tolerance and then make it stop while the tolerance is met, right? So basically that's the plan now. So let's see how we can implement this in C. So we first have to go to our terminal and then open our favorite text editor, so vim, and then we'll call this one bisection.c, right? So bisection.c, then we hit enter. Okay, so now we are in our favorite terminal. So we first include our standard input output, right? So the library, we include it, and then here, since we'll be making use of the absolute value, we would need to include the math library too as well. So include the math header, so math.h, right? And then we would have to define. So now to define something, or generally to use it, to declare something as a constant where we can use it anywhere in our program, we would have to use something called macros, right, in C. And then macros can be expressed as this. So you use the keyword define, and then mostly the rule of thumb is that you start their names with capital letters. Now this macro will receive some argument x, right? And then so we are saying that wherever you see capital F of x, what should you do? So we are going to put what it should do here. It should take the x, multiply it by itself, right, 3 times, and then so that will be the x cube minus x minus 1, right? So this is how we define the macro. So it means that we are defining our function. So wherever we the program sees capital F of x, right, it should compute this for us. So basically that's that. You could also define another macro, right, and then maybe call it the end, right? And then we said that to type the logical end, right, we would have to use double ampersand, right? So you could also do this, and then you could also decide to define the logical or, and then make it the double pipe, right? So that's that. So now once we have this, it means that instead of using the double ampersand or the double pipe, we could just type and or in our program, and then it will still run perfectly. So we use the macros if we want to make our code more readable or make it more flexible. So this basically does. Now you note that we don't terminate the macros with a semicolon. So you see that here we don't terminate them, and then we write them in caps to differentiate them, so that anybody that takes your code will be able to identify that no, you are using a macro here. The rule of thumb is to define them before your int main function. So now we can now include our int main, right? So int main, now we are returning void, so I will just put a void here. We are not returning anything, and then that. But then I would like us to use this as to define the bisection. I would like us to use functions, right? So we are applying functions here. So the bisection, in the end, we would have to return a float, right? That will be the approximate root. So we'll give it a float, and then we'll call this our function bisection, right? So bisection, or you can call it bisection. And then now this receives what? 3 arguments. So the first one could be a float, right? A float A, and then float B, and then a tolerance. So the float, so that will be our stopping criterion. And then that, bear in mind, what we are defining here is what we call the prototype, right? So we've declared the function prototype for the bisection function. And as I said, we can just come down here and do what? Declare our bisection function here, right? To make it look awesome. So here we could just use or call the bisection function. But before then, let's see. So we first have to go into our int main function and then declare some variables. So we can declare the, let's say, floats, right? We want our answer to be something, and then after declaring the answer, you can now come back here and say that answer, right? So answer should be equal to just the bisection, right? And then of what? Then you provide it with a number, let's say interval 1, 2, and then a tolerance of 0.00001 or something. Then you end it, and then in the end we want to print f our answer. So print f, so we want something like this. So the root is, the approximate root is what? So the root is percent f, since the answer is going to be a float, right? And then we want it to move to a new line, and we assign it the answer variable. Okay, so we have this. So the root is, then it will give us that. So you see that the use of the function is making our work quite easier, right? So in the end, we just have to just call the function and then supply it with some values. So the first one will be the lower boundary, that's the a. The second one will be the upper one, the 2, and then the next argument will be the tolerance. Okay, so now let's go down here and then define our function. Bear in mind that this part is inside the int main, right? So this is our main code. This is our function prototype. This is, we are declaring our macros. So declaring macros, right? So basically that's that. And then so that you can differentiate and know what this is going. Now we'll now have to come and then deal with our function. So I'll call this defining our creating our bisection function. So here we now define the bisection function. Bear in mind that whatever you put here should be the same as the prototype you gave it. So we gave it a name called bisection. This will receive a float a, right, and a float b, and then a tolerance, which is also going to be a float, so tall. And then here we will not end it with a semicolon, but then we'll now pass it or give it our argument. So now inside the bisection function, we first have to declare a variable called root, right? Root, and then this root will be equal to, let's say, root should be a float, okay? And then we have root to be equal to what? 0. We can initialize it by giving it 0. It doesn't matter, you can still decide to leave it that way. And then we'll need a stopping criterion to break out of our loop, right? So I will call it stop, right? You can give it any name you want, but then I'll give it stop. But then this is also going to be a float. No, okay, this should be an int. So int stop, then stop should be what? I could first initialize it by giving it 0, right? Now, so from here, the next thing I'll do is to now start with my loop, right? So while then we pass it, we give it a condition, and the condition we are using here is going to be stop, right? So while stop is equal to 0, right? While stop is equal to, bear in mind, we are using the double equal to show the equality or represent the equality operator, right? So you could still decide to use the equal to or declare it as a macro and use capital equal to here if you want to, but then I'll stick to the normal one. Then don't forget your parentheses, so you bring it here and then you inside the parentheses for the while loop, we now bring our conditions, right? So first, our first condition is if the absolute, right? Bear in mind, we declared we included the math library there, so we can say if what. Now we said we declared our function, so if capital F, right, of x, so here of a star, so times what, capital F of b, right, is less than 0, then it means that our root exists, right? So we should perform a particular task. Else if, right, our let's say else if f of a is equal to 0, right, is equal to 0, or so here we already declared our or, so we can just say capital or then the apps, so f apps, so to use the absolute value is f apps, so the absolute value of f of a, right, is less than what, the tolerance we gave it, right? So if this condition is true, then what should happen? It should perform a specific task here as well for us. And then else if, so this should be else if, sorry, so else if, and then we have what, else if again, right? This time around we check for what, the f of b part of the equation, so f of b, right, is equal to 0, or so or the f app, so the absolute value of what, we are using this or because we declared it as a macro. Keep that in mind, right? So if this is true, the absolute value of that is true, it's less than the tolerance, right, the tolerance we gave it, then it should also perform a specific task. Else, so it means that if this is not true, it means that what, our interval doesn't exist, right? So print f, let's deal with that side first. Print f and say that what, the root does not exist in the given interval, right? So basically we are saying that if this happens, it shouldn't, the root, it should print that the root does not exist in the given interval. And then from here we can just choose to, we have to terminate it, keep that in mind, and then we exit, right? We exit the program. So to use this exit to, would have to import some library called the standard library, else we will get an error. So for now, let's go and then check whether this code will compile without errors, right? I don't want any situation where we would finish building everything and then find out that there is an error somewhere and would have to painstakingly waste time to edit it. But before then, let's include the standard library. So include the standard library, so stdlib, right, .h. So now let's save it and see. We save our work and then we go here and try to compile. So gcc bisection .c, then we want the output to be in bisection .x, right? Okay, we have an error here. Stop. Okay, so we have to clear stop. For 0 and then float. Okay, we want the stop to be an int, so int stop equals 0. So let's go back and see. Okay, we don't have any error here, but that doesn't mean that when we run the code it will run. So let's go back down here and then provide the value. So now we said that if the functional value of the functional value at a, the product of the functional value at a and the product of the functional value at b is less than 0, then we should perform our bisection, right? So this is, it means that the root exists, so we would have to perform our bisection, and then we said that the bisection would let a certain xm, right? So we would have to define the xm as well, right? And then let it be a float, so x, so here I can call it x here, okay, and then a certain x m to be equal to, let's say, okay, let's not give it any value, so xm will now be equal to what? A plus b divided by 2. That's the bisection there, right? And then if this is true, then we would have to first find, so if what, the functional value, right? So f, so if f at xm, right, is equal to 0, or, so keep that in mind, or, so I want everything to be nice, so let me wrap all this part into a or, right, f apps. Remember that we are able to use this or because we declared it as a macro up there, so don't forget. So or the absolute value at that at xm, right, is less than the tolerance, right, then what should happen? It should return what? It should make the root, okay, root to be equal to the xm, right, and then change the stop to be equal to what? 1. or we could also make it 2 by 1. Assign the stop to 1. So we are bringing the stop to 1 because it will then make the stop in the while loop false, and then make the while loop to stop running. So basically that's that, right? And now let's come to the next if statement. Here we would have to terminate this line, sorry, and then so the next check would be what? Else if what? Else if, right, f. So if that is not true, if the xm is not equal, the functional value at xm is not equal to 0, then we will check what? Whether the product, right? So f of xm and okay, star what? F of, pay attention to the f. It's capital F because we declared that as a macro, right? So a, right, is equal to or is less than 0. If this is true, then it means that what? Our root will lie at the between the a and xm, right? So we would have to, we'll just reassign what? Our b to be equal to xm, right? So our b will be equal to what? Xm. And then that here we will make the loop continue running, right? Else if what? Else if the functional value f of xm, right, star what? F of b, right, is less than 0, then this time around we make what? Our a to be equal to what? Xm, right? And you have to end it. Look here, because it's just a single argument or a single statement we are given it, that's why I'm making all of them be on the same line. Okay, if you have a lot of things to do, you can just bring these curly braces down here and then work with it. Now, so we are done with the if, right? So it checks whether the root lies between xm and a, and then changes the b, checks, and then goes back here, and then what? Reassign a new xm to a plus b, right? So first it will come back here after getting a new b, it will check whether f is less, so obviously to come back to this and then get a new xm, come and check whether xm is equal to 0 or the functional value at that is less than what? The tolerance. If that's true, then it will assign the root to be equal to xm and then set the stop to be equal to 1 so that the loop can stop, or that we can break out of this loop. Else it will check which interval it belongs to now, whether it's the new a or the new xm, and then changes or gives it b equals xm or a equals xm, and then continue this process until this tolerance is met or the functional value at that is equal to 0, right? So now let's go here and then talk about the functional value at f of a equals 0 or that. So here, if this is true, then we should return the root of what? So we should return the root, right? We should say that the root is equal to what? It's equal to a, right? And then change our stop to maybe 2, right? And then when we get here, we should remember to terminate this line, right? We should change our root to be equal to b, and then stop to be equal to what? 2 here as well. So remember that this whole thing is an else if statement. This is the condition. The condition is in a parenthesis here, and then the statements are in the curly braces, right? So I just wanted to make this code more compact, so I decided to write it on one line. You can decide to bring them on, but as far as the statements are in the curly braces, you are good to go. Okay, so now let's try saving and run this and see whether we'll get any error here. Okay, there's an error. The stop, we didn't terminate the stop one here, so let me quickly do that. Let me quickly do that here. Okay, so now let's recompile and see. Alright, so we don't get any errors here, so let's try running our code and see. Bisection .x. Interesting. So you can see that our loop doesn't stop. So the fact that we are not seeing this means that the loop doesn't stop. So let's quickly do Control C and check what is wrong with our code here. So the reason why the loop stopped terminating is, first, let's see, we said that wow, but then we said absolute value of xm, and then we know that the absolute value of xm can never be less than that, right? Because we are not decreasing xm, so it should be the absolute value of the functional value, right, at xm. Okay, and then here too, let's see, the and then here we should also return, right? You have to return after the loop, and you have to return the roots, as we said, the roots. So return the roots, because if you don't return the roots you can't get an answer. So let's save this and then recompile. You don't get any error and run. So we see the root is 1.32478. so basically this is the approximated root given. Now let's go back to our main program and then change the interval and see. So what if we change the interval to 2 and then 3? What then happens? Let's save this and see. Once you save this and recompile and rerun, we had the root does not exist in the given interval. So yeah, our program runs. Bear in mind that you would have to, if you want to use the or and then the end, you have to declare them as macros, and then you'll be fine. So you can go ahead and then practice this by rebuilding the same thing for the second task, right? So you have to rebuild it for the second equation, the x cubed plus 2x squared plus x minus 1, and then try and post your answers in the comment section below if you are done with it. But if you face any difficulty, let me know in the comment section below. So basically that's that for this program. You could also try to tinker around through it and then see the edits that you can add to it. But for now, thanks for watching this one, and then we'll see you in the second one for the Newton Raphson. Thank you.